Hello students, this is Mr. Bob, and in this video, we're going to talk about significant figures. Before you watch this video, make sure you have focus notes set up on either a piece of paper or the digital template. The essential question for this short video is, why do we use significant figures in science, and what are the rules that govern them? So a couple of recommendations about taking notes in this video. Please avoid mindless copying. If you find yourself drifting into that zone, just pause the video, do something else, rewind the video, and refocus. Make sure you actively listen and selectively write down. You shouldn't be writing down everything on every slide. Think about things that I emphasize, especially, or that seem to stand out or be key to you. When I give you sample problems, please pause the video and take some time to work through them yourself. Make your brain struggle a bit, think about it a bit. Work as far as you can, and then start the video back again to check your answer. And if you're still confused after watching the video, identify it as a point of confusion on your notes, and remember to ask a classmate or me about it in the next few days. We have 3 learning targets for this video. I can explain why we use significant figures in science. 2, I can identify how many significant figures a number has. And 3, I can apply the rules of sig figs when I do math on 2 numbers. So let's talk about significant figures in general. An important thing in science is that we want to measure the uncertainty, or have an estimate of the uncertainty in our measurements, because pretty much any process we do in nature, any measurement device we use in nature, has some imperfections. For example, a meter stick often has marks at every millimeter. So there is an uncertainty in certain measurements. So for example, if we look at this blue line here that I've drawn on the slide, and I apply this meter stick that I've came up to it, notice there's a little bit of uncertainty in what I call this. Do I call this, it's more than 1.1 meters, excuse me, centimeters, but it's not quite 1.2 centimeters. So what do I call it? So this is kind of where we get into some rules that scientists use, and IB offers some rules that are common in science to help us understand what should we say in these cases to accurately communicate the uncertainty in our measurements. So there are 2 types of devices I want to talk about. Analog devices. For example, the meter stick we just talked about is an analog device. If you notice, analog devices are things where they don't have a digital readout, I guess is the best way of putting it. You're measuring in an analog way. For good analog devices, you can estimate the last digits. So in other words, when we're talking about the blue line back here, okay, notice it's between 1.1 and 1.2, so we can estimate that last digit. And in this case, because our meter stick is so big, we can go and say, we could say this line is 1.17 centimeters long, or some people might look at it and say, hey, that's 1.18 centimeters long. Both measurements are acceptable, okay? And again, that kind of goes to the uncertainty, because what we say then is the first 2 digits in that measurement are certain. We know it's 1.1 and a little bit more. The uncertainty comes from that last digit, okay? So that last little digit is what we call the uncertain digit, so to speak. And that is, when we write down this number, 1.17 or 1.18, we're communicating that we're really certain it's 1.1 and a little bit more. And the little bit more, that last digit, is the last significant figure, because that's what conveys our uncertainty. With digital devices, a little different. Digital devices, often you'll have a manufacturer specification that gives you information about its precision. If you don't have any information, then it's good to assume that the digital device is good to the least significant digits. So for example, this is a multimeter. And in this case, you would assume that this multimeter, given the setting they're using it on, is good to the nearest 0.1 volts, because that's the measurement, that's the last digit you can see there. I can't estimate smaller than 0.1 volts because there's no way for me to look beyond that digit. Okay, so if you want a definition of what significant figures are, I would say this. Significant figures are the reasonable number of digits that a measurement or calculation should have. And so, for example, if you use a meter stick to measure your teacher's height, like myself, what is the problem with the following statements? Statement 1, Mr. Bob's height is 1.85765432 meters. Statement 2, Mr. Bob's height is 2 meters. Well, again, think about the common meter sticks that you've used in the science classroom, and I've kind of given you a portion of it here. Hopefully, by looking at the markings, you can see there that the first measurement is just way too precise for what you're using. In other words, that first measurement is overselling the precision of that instrument. Because someone who looks at that measurement is going to think, wow, that student measured Mr. Bob's height accurately. They know it's 1.8576543. They're certain about those digits, and they're just uncertain about the last digit there, the number 2. And that's obviously not something that's feasible, not a reasonable measurement. On the other hand, this one, 2 meters, that is really underselling the precision of that instrument, right? Because if you say 2 meters, that means you're even uncertain whether it could be, my height could be as high as 3 meters, or it could be as short as 1 meter. And your instrument definitely allows you to be more precise than just saying 2 meters. So an acceptable measurement using a meter stick like the ones you commonly have in a science classroom would be to say Mr. Bob's height is 1.85 meters. So now I want to talk about the 5 rules for identifying the number of significant figures that a number has based on you're looking at a number on a piece of paper. So let's just jump right into it. With each of these, I'm going to give you examples, and I'm going to want you to pause the video and answer the questions for yourself and then reveal the answer. So first, the first rule, all non-zero digits are significant in a number. So there you have 3 examples. I'd like you to pause the video and answer the question, how many significant figures does each of these numbers have when you apply this rule number 1? Go ahead and pause the video. Okay, you should have gotten those numbers there, 3, 4, and 2. And if you have any questions, obviously, please follow up with me or a classmate. Rule number 2, all zeros between non-zero digits are significant. Notice there are 2 numbers there. Again, pause the video, apply that rule and the first rule, and come up with a number of how many significant digits each of these numbers has. You should have gotten 4 and 5. Rule number 3, filler zeros to the left of an understood or hidden decimal place are not significant. Okay, let's unpack this a little bit. Filler zeros. Notice you don't see a decimal point in any of these numbers, right? But there is an understood decimal point to be here, here, and here. So in effect, those zeros are just filling up the number so that you know where the decimal is. Okay, so go ahead and apply this logic now, rule number 3 and rules 1 and 2, to answer how many significant figures do each of these 3 numbers have, and I'll erase that. Hopefully you got 2, 1, and 1. Rule number 4, filler zeros to the right of a decimal place are not significant. Let's examine these 2 numbers. Notice these 2 numbers, the zeros here and here and here, are just filling in, backfilling, so to speak, so that you can put the decimal and you can indicate to anyone looking at this number where the decimal actually is. So those will be identified as filler zeros. So with that in mind, pause the video and identify how many sig figs these 2 numbers have. You should have gotten 1 and 1. And finally, number 5, all non-filler zeros to the right of a decimal place are significant. So notice you have 2 numbers there. Pause the video, apply all 5 rules, and come up with how many sig figs those 2 numbers have. You should have gotten 2 and 4. Now let's talk about calculations in significant figures. When you calculate 2 numbers, add, subtract, multiply, divide, there are certain rules to follow in order to determine how many sig figs the answer should have. Let's jump right into it. So notice there's 3 columns here. I'm going to give you an example. I'm going to apply the rule, give you the rule, then I'm going to give you some examples. The red is what your calculator is going to spit out. And then over here on the right-hand column is how many sig figures you should report in your answer. So when we're doing multiplication division of 2 numbers, what you want to do is you want to round your answer to the same number of significant digits as the quantity with the fewest numbers of significant digits. So notice I have one example here, 1.2 times 2. If I do that on my calculator, I get 2.4 centimeters squared. Pi times 2.75, you get that. And then you can see the final example looks like that when you get it in your calculator. So go ahead and pause the video and take a guess as to how many sig figs, the answer you should report for each of these examples. Oh, there's one more. There's the 4th one. And now I'll reveal the answer. So again, this is just simply applying the rule that you want to select the number that has the least number of sig figs. Notice in this case, the pi, anything like pi or e is considered to have many significant figures. One could almost say an infinite number, okay? The addition and subtraction rule. Round your answer to the same number of decimal places as the quantity with the fewest number of decimal places. So we have 2 numbers here that we're adding. This is the first example. Again, this is what your calculator would put out. And I want you to think about what should you report as the answer in each of these possibilities. So go ahead and pause the video again, work these through and think through what you think the answer is, and then continue. The answers are here. Some of you may have a question about this middle example. And this goes back to the fact that the way this number was reported, this 2000 number here, we have to assume these three figures, these three zeros are just filler zeros. So really, the least decimal place for this number is the 2. So that basically means that the least decimal you should have in your answer is also in this same column. Okay, that can be a little tricky. Just so you know, sometimes you'll see in IB problems, if they want to indicate that the zeros are significant, they might indicate something like this. I've seen this on a few IB problems. I don't really want to spend excuse me, a lot of time on it. But if you ever see this scenario, IB is indicating to you in this problem that the 3 zeros there are significant. Okay, that concludes this video. And if you have any questions, again, follow up with me or a classmate. Thank you very much.